Hello everyone. Good afternoon. It's about 12. A great set of talks before me. Rohit did a good job selling zkEVMs. So when I was sort of asked to give a talk here, I thought what should be the takeaway that I can give all of you in 7 minutes. So let me give you at a high level what I want you to take away before even I start. I want you to understand what zkEVM is and why it came about, like why people think about building zkEVM. So because all of you are developers, building is a very crucial part. So you should understand why zkEVMs are being built. That is the first point that I want to convey. The second point that I want you to take away is what are the trade-offs that are involved when we think about building zkEVMs. And the third is a special type of zkEVM that I'm personally bullish about. It's called Jolt. It stands apart from the other zkEVMs today, and I'll also tell you why. So let's get into it. So I want to start with what is a virtual machine. We all must have encountered this at some point of time. So pre-virtual machines, we had specific programs, calculators with a specific hardware. And then you could sort of just do the same program, and people were thinking, oh, this should be much easier to now. So I was basically, if I want to do sorting, I wouldn't go about building a different machine. So people started thinking about virtual machines. So a virtual machine would have a memory, it would have registers, it would have a CPU, a bunch of instructions. So you fetch instructions from memory, you fetch operands from memory, and then you execute them. That's what a virtual machine is, and how this helped. Now developers could come, they could just write programs with any language. They can write programs in C, Java, Rust, whatever you like. And then you have a compiler that sort of compiles it to the assembly code for the CPU. And then once you have the assembly code, the VM can sort of execute it. So this is how any program could be sort of envisioned on a virtual machine. And this is the natural transition even proof systems had. So before zkEVMs, proof systems were very purpose specific. So if you wanted to do an ERC20 transfer, your proof systems were built specifically for an ERC20 transfer. But then people were thinking, oh, why can't I just build a zero knowledge proof system for a VM? And that's what a zkEVM is. If you want to prove the execution for a zkEVM, that is for a virtual machine, which essentially involves three crucial steps. You have to prove that you correctly fetched operands from memory, you correctly fetched the instructions from memory, and then you stored the correct result in the memory again. So if you can sort of prove this for every instruction in a virtual machine, then you have a zkEVM. That's the bare bones of a zkEVM. And proving this requires a lot of mathematical effort. I won't get into the details, but I wanted to take this story back with you. And how does this help? Now again, the same story rehash. Programmers can just come and write programs. They don't have to worry about how proof systems are proven. They can just write programs and the execution environment. So since you have a zk proof system for the execution environment, you can generate a proof and you can verify a proof. So that's essentially what a zkEVM is. How does this help in the blockchain world? So before I come to the blockchain world, I just wanted to I told you there are trade-offs when we sort of think about proof system. Proof system does not come for free. You execute. Suppose you execute on a RISC-V machine. Everybody is comfortable with RISC-V. So suppose you execute on RISC-V, you would have sort of T cycles to natively execute this program. When you do a prover computation, you would have 10 raised to T6 cycles. That is like the overhead. It's about like 1,000,000 steps of overhead when you actually use something. What is the gain? The gain is that verification comes down logarithmically. So this paradigm makes a lot of sense in the blockchain space, because in blockchain there is a lot of repeated computation. The block producer is executing a program, and then all the validators are sort of rerunning the program. With a zkEVM, you would have the total compute coming down, and the total compute comes down when it makes sense for the overheads to come down completely. So if you actually do the math, it actually comes down if your overheads is less than the number of validator nodes, it will start looking better for you. So that's the picture that I want you to take back. So now let me just come back to all the virtual machines that these are like the list of virtual machines that are out there that I could find. So you have like a RISC-0, you have a SP1 by Sussex Lab, Zerion, you have Kakarot, you have KeroVM, you have Jolt. So these are like, and each of these zkVMs have an underlying VM that it's built through systems for. So most of them are based out of RISC-V, but then there are EVM based zero machine, ZK machines, there are MIPS based ZK machines and so on.